Hello students, hello everyone. Today we'll be learning about one experiment. The name of this experiment is the Marshall mix design, and this is the most important experiment I think in this transportation engineering lab. So let's not make further delay and let's start this experiment as soon as possible. So it will be a lengthy lecture, I think. So let's not waste further time. And Marshall mix design, let's to start with what is mix design. From mix design concept, from your materials course, you might be able to understand that what is mix design. Mix design is nothing but the proportion designing of different materials for constructing any structure, a particular structure. In material session we have learned about the concrete mix design. So while creating or constructing the structures, concrete structures, then the mix design of concrete is required. So in similar pattern, the concrete mix design may be used for the highway materials as well. And as we know that the pavements are mainly divided into two portions, flexible and the rigid one, as we know that. So rigid one will be similar to the concrete mix design as we have learned. So concrete mix design. So flexible pavement, for this particular thing we are learning this thing in transportation engineering session, just because flexible pavement is dealing with the asphalt or bitumen, as we know. So this one is flexible pavement, and asphalt content is required to be designed. So this asphalt content which we will be designing, that is called the mix design for the flexible pavement, and this is named after Bruce Marshall. The Bruce Marshall is actually the inventor of this design, that's why this is named after him as Marshall mix design. So you might have been thinking that the Marshall mix design is coming from, as it is related to US Army, but no, that is not the reason. Although US Army corporations have refined this particular test as well after the Bruce Marshall has given the basic properties or guidelines for this particular test. After that, this was refined by the US Army Corps, and finally it was designated as the Marshall mix design, Marshall method of mix design. So this is according to ASTM. If I say this was designated as some features were added by the US Army Corps, that's why finally it was called the Marshall's method of mix design. And this is according to ASTM. If I say it is designated as T1559, and according to the ASTO, as it is related to highway and state and highway department as well, that's why it is also guided in ASTO as T245. So both of these will be designating the similar test, the same test. Anyone can be used for consideration as reference. So what is our main purpose here? We will have a particular amount of aggregate. So we will have a particular aggregate sample. So using that sample, the aggregate sample we have learned throughout the sessional of this course, that different properties were there, flakiness, angularity, and different properties as well. So after validating all of the properties of those aggregates, finally we'll be choosing one aggregate for our mix design. And for this mix design with this aggregate, the amount of asphalt content which will be used with this. As we know that in flexible pavement, if I give example of a flexible pavement, this is a segment, for example, that consider this is a segment of highway. So to construct this pavement, we need what? We need different aggregates. So different types of aggregates with a particular gradation will be available for you there. So these aggregates will not be combined together if we don't use any asphalt content. So we need to add asphalt content as a binder, so that all the aggregates are binded together, and it will exert some strength to the roadway, and that's why while traffic will be going over there, it will be able to resist the loads. and that's why we need asphalt. So how much amount of the percentage of asphalt content should be used with this aggregate, that is our main concern in this design. Whereas in concrete mix design we were concerned about the water cement ratio, we were concerned about the aggregates amount, we were concerned about the cement, etc. admixtures were there. So that was in case of concrete mix design. But in transportation engineering, the flexible pavement design, that is it is relevant to the asphalt content. So if a particular aggregate we will be also designating this aggregate size as well according to their nominal size, and also with that particular sample of aggregate, the amount of asphalt content which should be used here, that will be called the mixed design proportion finally, which will be designed by us after this session. So this is the basic thing what we need to know before we start different terminology and the experiment procedure. So simply, if we say what will be the procedure for the experiment, will be simply creating a mold. Cylindrical mold will be there, having a particular diameter and height, and within that cylinder will be providing the aggregates. And finally, after providing aggregates, the mixture of aggregate and asphalt will be there. So we'll be creating mold. We'll be creating a cylindrical shaped sample. This particular specimen, the outer cover will be removed, and the only particular sample that will be solid cylindrical shaped pavement sample, which will contain the asphalt and aggregate, will be in our hand. So after processing, the procedure will be I'll be trying to discuss all in details as much as possible here today, although it will be a very lengthy lecture, I think. So finally, after obtaining this particular cylindrical shaped sample, we will be conducting the experiment over this for getting different feature values. The different feature values we will be also discussing afterwards. But before going to this experiment, we also need to know some terminologies we might have learned about or heard about this before, but we'll be discussing again today, which will make us convenient to understand all the way through this lecture. And before that, I need to give you some definitions regarding these aggregates, this bitumen, this specific gravity. To make you understand about this, I need to first illustrate a phase diagram which will make you understand these things properly. And before that, I need to give you a macroscopic view. I should show you a microscopic view of I should be showing a microscopic view of the aggregates. So whenever we are using aggregates, say this is one portion of aggregate. So in aggregates, there are these are called permeable pores. These pores, as you can see, and there are some impermeable pores might be there in this within this aggregate. So these are impermeable pores. So nothing can be going within this thing, that as these are impermeable, but this is a permeable pore. Also, if I add another aggregate here, if I add another aggregate here, think about it like this. So I can add another aggregate here, not like this. So if I add another aggregate here, so let's say this is another aggregate where there is again some impermeable pores are there, but you consider there's a little portion where it is also permeable. It is not impermeable in manner. This is permeable. Let's consider this is permeable. This is also permeable. Okay. So in addition to that, if I draw another aggregate here, let's consider this thing like this. So this is a set of aggregate, as we know. Now what we'll be using a bituminous content here. We'll be using bitumens. So the bitumens will be filling up almost all the permeable pores. It will try to penetrate through the impermeable pores, although it will not be able to penetrate through all the permeable pores, all through the impermeable pores. It will be extended up to some portions, but still then a large portion will be remaining there void. So these are all the permeable pores where the bitumen will be entering into. But you remember one thing, and there is air void. So the individual voids within the individual voids, if I say the individual voids within the aggregates, these are called all permeable pores. Okay, and these are called impermeable pores. These are within what? These pores are within the aggregate, individual aggregate. But while all the aggregates are combined in a manner, as you can see here, then the combined aggregate will exert some void. This void where the bitumen have been filled, this field of bitumen here, as you can see, these will be called the air voids. This particular portion will be called what? The void in mineral aggregate. The total portion will be called voids in mineral aggregates. The total voids. For considering this, let's consider no bitumen is there. So if you consider no bitumen is there, the total area, the total volume, that will be called the VMA, and the portion, this blank portion, if I just ignore this thing, the bituminous portions, if I ignore the bituminous portion and not these things, only the combined aggregate created some voids. So this particular void, we might use this as to say this is void in air void volume of air void, we can say. So this volume of air void and the volume of bitumen, in which is not absorbed. So if I further designate this thing differently, so this particular thing, if I add this thing differently, this particular thing, or this particular bitumen, or this particular bitumen, this bitumens, so all these bitumens which is absorbing through the aggregates, that will be called the absorbed bitumen or asphalt, whatever you say. So absorbed asphalt, this absorbed asphalt, if we don't ignore this absorbed asphalt and we consider the remaining asphalt within the void, so remaining this thing what we are talking about, this particular air void, this particular bitumen containing void, that will be called, this particular void containing bitumen, that will be called VFA, and that is nothing but the voids filled with asphalt. So these are the voids filled with asphalt, but these are actually pores, not voids. We don't say this as a void, rather we designate it as pores. within the aggregate. So pores that will be called the filled up pores with bitumen will be combinedly called, all those in combination it will be designated as absorbed asphalt. But the asphalt which will be filling the voids within the air void, the combination of aggregate, the void which will be filled with asphalt, that will be called VFA. And this VFA, that is actually indicating this bitumen, and the air void VA, that is actually indicating the still remaining air void after the bitumen fill, that in combination of VFA and VA, these two, VA and VFA, this is actually indicating nothing but the VMA, that is void in mineral aggregate, that is the total void. If there were no bitumen within this, the total void which will be resulting, that we'll call this as VMA. So now I think you will be able to learn the phase diagram easily, so I can share the this with you. So the phase diagram now I will be sharing with you, so now you'll be able to understand very easily. So this one, the VMA, this is nothing but the total void in mineral aggregate, but some of this total void in mineral aggregate is filled with VFA, that is filled with asphalt. So if there are no asphalt, this is the total asphalt content. From this one to this one, this is called the total quantity of asphalt. So within which it can be further divided into two portions, one of which will be filling the voids, and one of which, this portion that is called absorbed asphalt, which will be absorbed by these aggregates. So within aggregate, this asphalt will be going, the absorbed asphalt, the remaining asphalt which will be free in the void within the combination of aggregate samples, resulting void, that will be called the VFA, the void filled with asphalt. And this void filled with asphalt in combination with VA, the void, air void, volume of air void, in combination of these two, it will be resulting in void in mineral aggregate, that we call that if there were no asphalt there, then the total air void which would result, that will be called the VM, volume of mineral aggregate. And this is the total quality asphalt. Again I am saying this is, and this can be designated as VV as well, the volume of bitumen or asphalt. And this is VAB, as we are again saying, this is absorbed asphalt, so volume of absorbed bitumen. And this is VAG, this is nothing but the volume of aggregate, the actual solid volume of aggregate in the this is the actual solid volume of aggregates we are talking about. Okay, so another thing we are taking in consideration, that is the impermeable pores. So we will be always considering this thing, just because this will be remaining impermeable throughout the experiment. That's why always consider this impermeable pores there, therefore no asphalt or water can penetrate through it. Another thing what you should be remembering, that in basic concept, that as much the bitumen can penetrate through this, but if we had used water instead of bitumen, the water would be able to fill the total pore. The total pore can be filled up by the water, that is possible, but due to viscosity and all other factors, the bitumen contents, the bitumen portion will not be able to penetrate through it. And as we have limited percentage of asphalt content we are using, that's why not necessarily, and in general, the bitumen will not be able to reach the at the final portion of this impermeable pores. That's why some portion will be still remaining in empty pores, although within the permeable pores, although the bitumen will be penetrated through up to some extent. Still then there will be remaining portions as well, as you can see. But if we use water in this aggregates, then the water will be able to penetrate through this, and it will be going through the farthest portion of this pores, although the impermeable pores will be still impermeable for bitumen and water, whatever we use. Impermeable will be impermeable in all cases. So from this basic concept, some things that will be generated here. So VFA, VMA, these things are clear to you, I think, by this time. But the additional thing now I'll be discussing there, that is the specific gravity of aggregates or the mixture, different aggregates or mixtures or individual aggregates we will be discussing about here. So specific gravity we are saying. So there will be different types of specific gravity according to our concern. So we will be focusing on mainly three. First of all, we will be learning mainly three specific gravity: bulk specific gravity, bulk specific gravity we'll be learning. After that we'll be watching apparent SG, and finally we'll be watching the effective SG afterwards. So these three things we'll be learning first, and also if we can we'll be focus on bulk SSD as well, but not our concern. And after discussing these three, we will be deducting this particular concept from our this experiment totally, just because we don't need this. Okay, so bulk specific gravity, if I designate this will be specific gravity, bulk specific gravity. So bulk specific gravity might be of the aggregates and also maybe of the mixture. So if I talking about the mixture means the mixture of aggregate and the bitumen. This is called the mixture. If I am concerned about the mixture of the aggregate with bitumen and the bulk specific gravity of that, then we will be talking about the GMB. So bulk specific gravity of the mixture G, that is this one, mixture. And the effective specific gravity will be designating this thing as GSE, the specific gravity, bulk specific gravity. Okay, and this might be designated as GSA, but we will not be concerning about this. So let's discuss and clarify this concept first. That will be making you easier to understand these things further. So to introduce this thing first, I need to show this. As you can see that first of all the terminologies must be clarified there for you. So as we have discussed, there will be some impermeable void, as you can see. So we are rather will be preferring to say this as pores to make it understand, as we are using void for designating the air voids in combination of different aggregates, the resulting void, that is we are using void. So better to use pores, although there is only one aggregate. That's why if we use void or pores, that doesn't matter for us. So this is aggregate in grayish color. You can see the aggregate, the asphalt binder, as you can see the blackish portion, the total thing, and the impermeable void, as you can see. The permeable void is the dotted green line. Within the dotted green line, the portion which is permeable, the total, say these portions, it might be filled up with asphalt, and some portions may be remain unfilled with asphalt. So all of these portions will be called permeable pores, and whereas the impermeable, as you can easily see from this figure, and asphalt binder, aggregates, all these things are clarified to us. So now if I say what is bulk specific gravity, first of all, if I say what is bulk specific gravity? Bulk specific gravity is always the specific gravity is what the volume, the mass of this mass of a particular volume will be used. So in this, all these cases which we'll be discussing, only except the bulk SSD specific gravity, we will not be discussing it here. But all for these three, the mass will always be the solid mass weight of the aggregate, that is the reddish portion, that is the grayish portion, that was the grayish portion previously. So this reddish portion excluding all other voids and impermeable pores, the solid portions which wet oven dry condition wet will be getting, that will be called the mass, which will be used for our calculation. This is the actual mass which we will be always using. If I say mass or weight, whatever it is, it doesn't matter. So the mass which we'll be using here, this is the solid mass in all cases. For bulk specific gravity, the volume, the main difference is the volume which will be used for taking the equivalent water volume, weight of volume, equivalent volume weight of water. So in the case of bulk specific gravity, although the mass considered is the solid portion of the aggregate, but the volume will be considered as the total volume, including the permeable pore volume and the impermeable pore volume. Impermeable volume, as you can see from this figure, and permeable pore are also, voids are also seen here. That is cordoned with the bluish boundary. So although all these things you can see here. And also, if I say that we are only considering this particular definition is only valid when we are using one thing, if we are using the specific gravity for aggregate. But if we are using the specific gravity, bulk specific gravity, for the mixture, bituminous mixture, then this mass will be changed. This solid mass, the reddish portion's mass, in addition to this solid portion, reddish portion of mass, we will also have to include within the greenish cordon the bitumen portions, which will be also included in this as well. And therefore that will give you the bituminous portion as well. If I consider, that will also give you the bulk specific gravity for the bituminous mixture. Whereas if you just consider for the aggregates, then you will not have to consider the bituminous portion, rather you will be only considering the mass of only the aggregate portion. But in case of volume, it will be same whether it is mixture or whether it is the bulk specific gravity of aggregates only. It doesn't matter. The volume will always be taking as the cordon portion of the bluish cordon, as you can see here. So how we will be taking this bluish cordon portions volume as water? So let's consider for the mixture first. Aggregates will be automatically learning. In case of aggregates, you will be just ignoring what? You will be ignoring the aggregate portion. That is the only difference while taking weight. In all other things are being similar. So how to take this bulk specific gravity, how to get it? Let's watch. So for considering this thing, I will be saying that you will be taking the weight of the sample. This is the particular sample, and don't think this is a cylinder. This is a cylindrical shaped specimen. The mold is removed already, so we have already this portion, this aggregate sample, within which it is binded with bitumen. That's why we are calling this a mixture. Okay, this is mixture. So we'll be taking the weight in air first of this mixture. That will be called WA. You will have to also use this thing in your experiment as well. That's why please focus on this seriously. So this is WA, that is the weight of the total sample in air. Then after that we will be submerging this thing into the water for at least 24 hours, and after 24 hours what will happen, that the water will be penetrating through all the permeable pores in this aggregates beyond the bitumen, as bitumen cannot go up to the furthest point of the permeable pores that water will be able to go through. So therefore what will happen, that if these are the aggregates, say these aggregates, this will be the aggregates, these will be the aggregates, although some impermeable pores will be present, that is not our concern, but the bitumen will be penetrating through. some portion of this. So to show this bitumen, let's show this bitumen with this. So there will be bitumen, so bitumen will be going up to some portions there, up to some portions, and the voids obviously will be filled with some voids will be also filled with bitumens as well. So, and the pores as well, permeable pores. So what the water will do, water will be at 24 hours, after 24 hours water will be penetrating through all these pores. It will be totally filled up with water. It will be totally filled up with water, as you can see. As you can see from there, all the impermeable pores will be remaining impermeable throughout the experiment. Okay, also as it is submerged in water, you can say water all throughout there. So if we wet this specimen, in water, we will get WW, weight of specimen in water, but this weight will give you what? A reduced value than this WA, just because of what? The reduced weight, the WA minus WW. If there were no water penetrating through these portions, let's focus on this. If there were no water penetrating through these portions, say for example there were no permeable pores and these pores were not filled up by water, then if we consider that these portions were not filled up with water, then only the remaining portion weight in water might have been this one, this WA weight in water, subtracting from the water weight WW. This would give you the actual weight of water. So this is actually weight of sample in water, this one WW. But when we deduct this thing, just because it will be removing the solid volume of aggregate, will be remaining this the weight it will be losing, that will be equal to the equal volume of the water weight. That's why the reduced volume WW, if I deduct it from the air weight, then you will get the equivalent volume weight of water. So weight of water, that is of equivalent volume. So if there were no such pore filled up with water, then you might have got the actual specific gravity, no doubt about that. But as the water has penetrated through this and this, and you have measured the weight including this water, so we need to also remove these water portions as well. So what we need to do, the solid portion of water will be, that's why what we'll be doing, that we will be removing this particular sample from the water. So if we pick up it from the water, and what we'll be doing, we will be drying the surface. So after that, immediately we will be drying the surface. So surface will be totally dried with by any means. So if we immediately dry the surface, then the water will be still within the pores, permeable pores. It will be penetrated through that. Still after that, it will be penetrating through these pores. So therefore, if we just clean and dry the surface and then wet this aggregate in air, after that you will be, then already the aggregate is in saturated condition with water. As it is saturated in water, although surface is dry, but the inside the pore is filled up with water, so the measurement you will be getting, that will be WS, this is the SSD weight, saturated surface dry condition weight of this aggregate, which will be greater than WA, up to which extent this particular 3 water portion additional weight will be added to this WA to get this WS. So this is the difference between WS and this WA. So why we are getting this WS? So we will be deducting WS, we will be deducting WW from WS, not WA. So this portion will give you what? This portion is actually WS, means including these waters as well. So it will be including WA with the permeable pore volume and this WA means solid aggregate portion, solid aggregate, and the permeable portion as well. Bitumen is already included as we are dealing with mixture. We say it is mixture, so forget about bitumen. We are just considering solid aggregate, and also bitumen included already by this time. But in addition to that, the permeable pore volume is weight of water is also included there. So when we will be deducting WW, that will theoretically from WA, if I deduct WW, it will be giving you the solid portion, this solid portions equivalent volumes weight. But when we are deducting from WS, so this additional permeable volume of water is added. So we are considering as if, although these aggregates have some permeable pores, we are also although this portion is a pore, but in this case we are assuming that the weight is, although this is the solid portion weight we are taking and this is air weight, but in case of bulk specific gravity we are assuming that as if this void is also included as volume in this solid portion, although it is actually not. So therefore, while considering volume, we are taking this also impermeable pore, also the permeable pore as volume, although the weight is only the solid portion, just because this portion will not give you any weight just because of air. These portions are air, so no weight for this. So therefore we will be getting the weight for only solid portion, but we will be considering volume for both permeable, impermeable, included volume of the solid. So that's why we will be the GMB, that will be equals to weight of the solid volume, weight of this aggregate in air divided by the weight of this the saturated weight minus the weight in water, which will actually give you the weight of water not equivalent to only the solid portion, but also including the volume of impermeable and permeable pore as well. That's why we are calling it as GMB. I think you will understand, you have understood what I am trying to mean here. So let not give further time in this. This is GMB, how we will be calculating. Already the procedure has been explained here, so I will not be repeating this thing while describing the experimental procedure afterwards. In theoretical portion I already have completed this thing. And what about GSA? Just forget about GSA, just because apparent specific gravity will not be using in case of our experiment, but still to clarify you, I am just showing you what is apparent specific gravity. In apparent specific gravity, the only difference is this: in apparent specific gravity, the volume of the actual aggregate portion will be used, whereas in bulk specific gravity, as you can see, the water permeable void, it is called water permeable void just because in addition to bitumen, the water will be able to penetrate through the farthest point from including this bitumen. That's why it is called water permeable void, not asphalt permeable voids. So the water permeable void is actually this remaining void and also this bituminous filled void. that is poured within this aggregate. So all this will be included in water permeable voids and aggregate particle. So while considering volume, we have considered the water permeable void as well. That's why we have taken the saturated surface dry void, as you have seen just before this. But while apparent specific gravity, we simply just take the aggregate particle volume, this particular volume. So when we'll be considering this particular volume, in that case that will be called the apparent specific gravity. This is very simple, but we have shown you the complex one just because we'll have to use that, but we will not be using the apparent specific gravity while conducting the test. And the bulk SSD specific gravity, let's not discuss it there, but just because it will have no use in our case. So let's use the effective specific gravity in here. So what is the difference of between the effective specific gravity and the apparent specific gravity, or the bulk specific gravity? As you can see, always as usual, we will be taking the solid portion, the oven dry weight mass, as mass. That is, mass is always these solid portions will be using. But in case of effective specific gravity, we will be considering what? In case of bulk specific gravity, we have considered the total pore, the total permeable pore, as you can see, including as I have just said, that water permeable pores or voids indicates the total voids that is already remaining and also filled up with void. These two in combination, it is called the water permeable void. But while we will be deducting the absorbed asphalt, that is the blackish portion within these pores, deducting from the water permeable voids, this will be resulting only the remaining voids within the permeable pores after the asphalt has been filled. That particular portion of volume will be added to the solid volume of the aggregate, and this will be used for calculating this volume's equivalent weight of water will be used to calculate the effective specific gravity of that particular aggregate. So that particular aggregate, in this case, just remember, as we are as you can see, as we are deducting the absorbed asphalt, and all asphalt has been deduced and ignored throughout this thing. That's why we'll be saying that this is absorbed asphalt. And absorbed asphalt, in this case, absorbed asphalt, as it is totally ignored, that's why we'll be saying that this is actually effective specific gravity of, it will be called the effective specific gravity of, not the mixture, rather we'll be using the term as all aggregates. So we'll be saying of all aggregates, in this case all aggregates. Okay, so this will be called the effective specific gravity of all aggregates. In previous case, a bulk specific gravity, it might be of aggregate or it might be of bitumen. It will be depending on the weight which we are using. But in effective specific gravity, if we are taking the weight of as we are totally ignoring bitumen, so while weighting in water, in previous case the weight of water, it was actually was of mixture. If we were taken the aggregates, that would have given us the if we had taken only the weight of aggregate instead of mixture, in case of previous bulk specific gravity, that would have been the bulk specific gravity of the aggregates, dry aggregates. But as we have used mixture, that's why it is called the bulk specific gravity of the mixture, bituminous mixture of aggregate. And in case of effective specific gravity of all aggregates, we will be taking the weight of solid only aggregate portion, not the bitumen. And also while calculating the volume, we will be taking the volume the remaining volume after the absorbed asphalt is there, so we'll be ignoring the asphalt totally from there. The remaining void will be used, so that's why that will be called the effective specific gravity of all aggregates. That is the designation we are using here. And to give this particular example, we need to formulate this like PMM. This is the total mixture in percentage weight. If I say this is 100%, PB is the bituminous percentage, say let's use this is 4%. If we use then PM, this is PM minus PB, this will give you PS actually. Then PS is nothing but the all the sum of aggregates. So if we use three types of aggregates, coarse aggregate, fine aggregates, and the filler within the pores after the coarse and fine aggregates have been placed, then also we can use for coarse aggregate we can further divide this P1 into different portions as well. But in our case we'll be designating the coarse aggregate individually. All the aggregate sizes we can the range will be calling the coarse aggregate, this will be the fine aggregate, and this will be MF. So in these all these percentage of aggregates will in summation of all this will give you the total percentage of aggregates, and this is total percent of bitumen, and these two will be resulting in total mixture percentage, that is the 100%. To explore this thing in formulation, if I say the formula will be like this: the PMM divided by the GMM. What is GMM? GMM will be nothing but the specific gravity of the mixture which we can use. GMM will be the maximum specific gravity of all mixtures. GMM, the maximum specific gravity of all mixtures. So mixture is there. So this is the total mixture, total specific gravity. This is the total volume of the mixture that we are concerned about, the total mixture of the volume. So this PMM by GMM is equals to VMM. This is actually equals to PS divided by GSE, the specific gravity, the effective specific gravity of all aggregates, and that's why this is all aggregates proportion is there, plus percentage of bitumen divided by the specific gravity of bitumen is there. So this is in terms we can say this is the volume of bitumen, and this one is nothing but the equivalent to the volume of all other aggregates, so VS. So from this you can easily understand that. So while taking the total volume, if we deduct the bitumen, not necessary this bitumen is within absorbed by the aggregate, or it is within the void space of combined aggregates, it doesn't matter. So let's think about this. This is aggregate mixture, aggregate mixtures is there. If aggregate mixtures are there, then we will be totally ignoring the bituminous portions. Although these are bituminous portion, as you can see, bituminous portions, bituminous portion might be filled in void, and also the pores, permeable pores. Okay, so the total bitumen portions, whether it is it doesn't matter whether actually it is the total bituminous portion, whether it is in air void or within the absorbed portion, it doesn't matter. The total bitumen is volume of bitumen that is totally distinguished and differentiated in this term, the volume of bitumen, and the remaining portion, this portion, the remaining void portions including these remaining pores and including also the impermeable pore. These aggregates, it doesn't matter whether it is a fine or coarse aggregate, it doesn't matter, but throughout this total aggregates we will be using it as the total volume of S, and for using that this as this permeable and impermeable pores excluding the absorbed bituminous volume, the total volume has been used for the specific gravity. That specific gravity is called the effective specific gravity. That's why it is as it is used and as it is shown there. So now I think it is clarified, so we can proceed further for the experiment now. And one thing you should remember, that you should not be confused with this thing. Although I have used to express volume, although you know that there should be the value of density rho should be used with these things to get this, but for equivalency, to make you understand about the equivalent concept, I have used this volume V to make you understand about that. But all other than this, the concept is similar, so you can make use of this for making it more comprehensive. So however, now we will be discussing about another formula that I have left while discussing before, that I said that what about the bulk specific gravity of the aggregate, that will be called GSB. Although we have learned about GMB last in the mixture, but GSB will be the, as we know that GSB, I have said before that this was for the aggregate only. So bulk dry specific gravity of the total aggregate, GSB will be bulk specific gravity of the total aggregate. Okay, so total aggregate, that will be GSB, and that's why. So that's why while using GSB, we will be using the formula for the aggregates only instead of mixture bitumen. Ignoring the bitumen, we'll be using the formula. So for this, if I want to write down the formula of GSB will be like P1, as we know, P1, P2 and P3, three types of aggregates will be used. The total portion of these three, PS also known as PS, and individually volume of all these three. So P1 divided by G1, P2 divided by G2, and P3 divided by G3, where this G1, G2 and G3 are the specific gravity of P1, P2 and P3 respectively, and all these G1, G2, G3 are bulk specific gravity individual for individual materials. So G1, G2, G3 are bulk specific gravities for individual coarse, fine and MF, and therefore the total volume, if it is divided, used to divide it for PS, we will be getting the GSB, and this is nothing but the bulk specific gravity of the total aggregate. So you can use this formula as well. However, we'll be learning some further formula regarding this thing, although we have learned the maximum things here, but we'll be learning about this further while showing the experimental calculations afterwards. So now we will be getting into our experiments. So if we getting into our experiments, first to start with, I would like to say that as I have started before, we will be needing some features. In general, we use 6 features, as you might have known about this. 6 graphs will be used for this Marshall mix design method, and all these graphs will be plotted against asphalt content that will be required for us. Okay, so the patterns of the graphs, if I want to give an example of this graph, all these 6 graphs, typical graphs, which might also appear in your exam, in your quiz as well. So typical graph patterns, you should be able to draw all these patterns as well. So first of all, if I want to show all these 6 features, please focus on these 6 features. First one is the air void percent, that is nothing but the VA percent, air void, volume of air void percent in this y-axis. All the axes are as you can see, that contains asphalt content. So this is VMA in percent, this is VFA in percent, this is unit weight in pound PCF, the stability and flow. These two things we need to know about now. Unit weight you know by this time, and all these three additional we know by this time. But the stability and flow, what about these two things? So let's define the stability and let's define the flow. So if I want to define the flow, what is flow? So during flow, so we'll be doing what? This will be the cylinder specimen, which will be finally placed into the compacted equipment. Then we will be applying load upon this from the Marshall mixed design apparatus, the loading machine. So we'll be giving loads like in this pattern. So while giving loads, it will be the maximum load which it will be able to, this specimen, this will be able to, the cylindrical specimen will be able to take or resist. That will be called the stability value. And before failure, so failure will be automatically indicated by the apparatus or the machine equipment we'll be using in Marshall mix method. So the stability, this will be actually at a defined temperature. So at 140 degree Fahrenheit temperature is fixed, or we can also say 60 degrees Celsius probably. This might be 60 degrees Celsius. So at 140 degree Fahrenheit, that is fixed, and the loading will be applied here at a rate of 2 inch per minute. So that will be the loading rate, 2 inch per minute. Deformation rate will be applying over this. So the maximum, the loading rate is 2 inch per minute. It will be compressed. So therefore the maximum load that will be carried by this specimen before failure, that will be called the stability. And the stability in general we use this in Newton, particularly as if we are using say USA method. So yes, it is provided by USA, so generally we also use Newton, but also we use pounds as well, as you can see here. But in general Newton is preferred. So it will be depending upon your experimental setup or your requirement, which amount or which units we are dealing with. That is important. Other than that, it is applicable universally, so no problem with that. So however, the stability, that's why this will be the stability. And what will be the flow? Flow, by definition, the flow will be the there are different things which will be affecting the stability value of the specimen. I am not going to discuss this. This will be discussed in your theoretical classes, so I am not focusing on these things. The flexibility is measured in the term of flow value. That is our concern. It is actually indicates the flexibility. Okay, so if I say in very short that this flow value is nothing but the this will be the deformation which will this specimen will exert before the failure at the stability value of load. That will be the value of flow in this case. So the flow in particular, we use this in a particular inch, as you can also see from the graph above, that is shown in 0.01 inch. So in general the flow is shown in 0.01 inch value unit. Inch unit. So for example, if you get the reading, the deformation, you get say 8.18 inch, then the flow will be 18 unit. Unit means this unit is this 0.1 inch 01 inch unit. Therefore, if you multiply this with this unit, you will get 0.18 inch. So this will be our flow value. So this is 0.01 inch, that is our flow value. We can also express this in millimeter as well. We can also express the flow value in millimeter as well. Keep remember these things, that either in millimeter or in inch, whatever you use, you can use for the flow values. So it will be depending upon which unit you are actually using. So I can say that the flow value we can also use in units of 0.25 millimeter. Also we can say 0.25 millimeter unit can be used if unit is used for flow value. So it will be depending in which unit you are calculating all these things. So if you are calculating in 0.01 inch, then it will be like this if the value is 0.18 inch, and in similar case if you obtain the millimeter value or convert it to millimeter, then the flow value of 0.25 millimeter unit you will have to convert the values into. So therefore you will be getting the flow value. So again I am saying the flow value is the total movement or displacement occurring in that particular specimen between first of all no load was given, then the deformation will be treated as 0, and after load has been applied and the stability maximum value before failure has been obtained, the deformation will be again taken, and then this differences, if it initial value is recorded as 0, then the differences between these two deformation will be taken as the flow value finally. Okay. Also in some cases we use gauges. So gauge give some readings in experimental setups. If our apparatus will give some readings, in some cases readings are given in different units. So in general say our readings are given in multiplied by 10 to the power minus 3 inch. This unit might be there for readings. So if these readings are in this particular unit, then if you get reading of 180, then you will say this is actually 0.18 inch. And in that case, if you want to convert it into 0.01 inch unit, then you will have to divide the reading divided by 10. So that's how you will have to make approach for this. So whatever, I don't think this will make any complexities. Just what you need to know, that this particular pattern and which unit you were using for this, and the dial gauge reading in which unit it is giving it, you should be able to know that. Okay, so what should be our preparation? So there are some criteria for this experiment and pavement. There are 3 types of pavement may be there. So in this particular experiment in Marshall Mix Design, it divides the pavement, flexible pavement, into 3 types based on the traffic's movement. So based on traffic, 3 types are there. So first of all, one is the light traffic or low, and medium, and finally the heavy traffic. So all this indicates actually depending on the number of traffics moving towards this over the pavement that is predicted from the analysis or experimental data or prediction which will be getting, that will indicate whether this will be designed for whether heavy traffic or low traffic, medium traffic or light traffic. So this is nothing but based on the EAL. So you will have the guidelines. If it is less than 10 to the power 4, then light. If EAL is 10 to the power 4 to 10 to the power 6, then it will be called medium. then it will be called medium, and if you see this is greater than 10 to the power 6, then it will be called heavy. So these three are the conditions whether this is light, medium or heavy, and based on this you will have to apply the compaction load before the specimen is finally prepared for applying load to analyze stability and flow. However, so we need to apply compaction after the specimen is prepared. So how we will have aggregates, as we know, we have a sample of aggregates from where we need to know another definition, that is the nominal aggregate and maximum aggregate size. So nominal aggregate size and maximum aggregate size, these things we need to understand. Okay, so if you have a gradation of this particular aggregate, we have to conduct the sieve analysis first with the standard sieves, and after conducting the sieve analysis you will be getting the percent retained values. You can write down those things in a table, as we know that how to you know by this time how to complete those tables, sieve analysis tables. So let's give an example. I will be giving an example for this. I will be giving an example for this. I will be giving an example but before that I need to import that particular table to you. So I will be importing that particular table here for your convenience. So this will be our gradation, for example. So there are standard sieves. So what is the nominal size? The nominal size is designated as the designation. To designate this particular aggregate sample, we use the nominal size. What is nominal size? Nominal size is nothing but the first sieve. The first sieve to retain greater than 10%, that will be called the first sieve to retain 10%, one greater than. So one sieve greater than the first sieve to retain 10%. So what is the first sieve retaining 10%, more than 10% from this sieve analysis? You can see the first one is this one, which is retaining greater than 10%. So greater than 10% is actually 3/8 inch or 9.5 millimeter, but nominal size is called the one sieve greater than the first sieve to retain 10%. So nominal sieve here will be nothing but the 19 millimeter, that is this one. So, and that's why this is also called the designated, means designation is 19 millimeter. And what will be the maximum size of aggregate? That will be one size greater than the nominal size, the nominal. So in this case nominal size is 90 millimeter, so the maximum size will be one greater than that. So you might have greater amount, greater than 25 millimeter available in your calculation as well, and those might be retaining some sieve analysis. From those you might be getting some of the values as well. That is possible also, but in that case we will be ignoring those things and we will be taking this nominal size, the first retaining greater than 10% as nominal size, one more than that will be nominal size, and one more than that will be taken as the maximum size. And as the maximum size is this one, so we will be calculating all things from this. So maximum 1 inch, we will be always taking it as all all the aggregates passing through this 1 inch will be taken as in the first maximum size. So nothing it will be retained here. You will see this is not, actually this one retained, although this is cumulative. Just ignore this one. This is greater than 10%, so that's why we are treating this one as nominal and this one as maximum. So always maximum will be retaining 0.1, as we will be expecting in maximum sieve size all the aggregates will be passing, and all the particle samples will be retaining in this sieve size, particular sieve size. And the maximum sieve size we will be just ignoring from our calculation when we will be taking the retaining 0 in maximum, and all other things will be similar like this. So that's why we say the maximum sieve size that will be 1 inch or 25 millimeter, actually the percent retained individually, and the nominal size will be 19 millimeter. And that's how the gradation has been completed. The total 100% is there. This is MF filler, so that which will be remaining in the pan after analysis of sieve of number 200 or 75 micrometer. The remaining particles will be designated as MF, and that is nothing but 5%. That is not that is also considerable in amount. So this one will be taken, and total this will be calculated throughout this. The total weight in gram that should be taken into consideration. Now one thing, the percent of asphalt content we are saying from the very beginning of our class. So what is percent asphalt content? Percent asphalt content is nothing but the total, the percent of asphalt with respect to the total weight of mixture. So remember one thing, not the total weight of aggregates, total weight of mixture. So we might be expressing the asphalt content in terms of total weight of aggregate. Also we can express in terms of total weight of mixture as well. So if nothing is mentioned, in generally we always will be using the total weight of mixture. So if I say for our experiment we will be using 4% asphalt content, can you calculate what will be the asphalt content in gram for our this particular sample of aggregate which we are dealing with? So in that case, the mistake most of the time you do, that is you just usually make the 4% of 1155 and just make it and use this as the asphalt content, but it will be wrong in this case just because we are using the total weight of the mixture. That's why the weight of asphalt content plus the weight of aggregate, that is 1155, that will be the total weight of mixture. And as this is the total weight of mixture, 4% of this one will be the asphalt content. This will be actually this asphalt content, 4% of this one. So you will have to calculate it like that. Okay, so if you treat that this value is x, then you will be using 0.04x plus this 1155 equals to x, and from this equation you will be calculating what will be the total weight first, and then what will be the asphalt content in gram. So after that you will get that for this particular aggregate sample you will be using this particular gram of asphalt content to mix this to create the final specimen, the sample, mixture sample. And that sample, particularly if we have a cylinder. In the very beginning we have said this cylinder will have a particular dimension, obviously, which you need to remember as well. I am just mentioning this thing, that what will be the diameter and what will be the height of this. So what will be the diameter and what will be the height. So I am saying that this particular diameter, although this figure is not representative, rather we just deduct this one. If we want to show the representative cylinder sample, that will be like this. So just because the diameter will be larger than the height which we'll be using here. So in case in the material sessional, you have seen that in a cylindrical test for applying loads, that where we need to maintain these things less than 2, just because there might be adverse effects for this. Otherwise we will have to use different correction factors you have seen there, just because of platen restraint effect or difference effects were there, height by d diameter ratio were there. But in this case we have no problem for this, just because our diameter will be well large amount than the h, so no admits of h by d equals to 2, or rather it will be always less than 1. You will be watching there. So what will be the diameter and what will be the height of the specimen? In general, if I want to say this, what we use generally is the cylindrical height. We generally use this particular height will be okay, height will not be as large as although no, sorry, I have just made a mistake. The height will be obviously larger, but not as large as it will be creating greater than 2. It will be always less than 2, as therefore we should not be applying any correction factor to maintain this thing. With our height will be obviously greater than diameter, but not as much, so it will be resulting h by d ratio greater than 2. So therefore the height and diameter will be like this. The height is, we use generally 102 millimeter, we can say, or it may be 4 inch, and the diameter we use, we can say that this will be 64 millimeter in case, or 63.5 if specifically I say. This is what we should be using. Okay, I have made again the mistake I have made. I was right in the first case. I'm very extremely sorry for that. I was right in first case that the diameter we'll be using, that will be greater than the height. So there is no admit of h by d ratio greater than 2, rather it will be always less than 1 in fact. So diameter, and this is the height. So height will be 63.5 millimeter, and whereas the diameter will be 102 millimeter, that is equivalent to 4 inch actually, and this is maybe 2.5 inch we are dealing with the height. So therefore the height by d ratio will be less than 1, so no problem and no correction factor should be used here. So as this is the final height which we should be filling it with, and why we always target, just keep remembering one thing, that we always target for the total mixture equals to 1200 gram. This is our main target. Why? In practical sense, we always see that as these particular dimensions are fixed for this Marshall mix design, we always see that 1200 gram always fulfills this height, 63.5 height, this 63 height. So if it is not actually 63.5 millimeter, then you will have to apply correction factor, as all other things are calibrated based on this 63.5. There is a chart for this which we must need to apply. If we don't have height equals to 63.5, then we will have to apply the correction factors, and about these correction factors I will be discussing here now. So the correction I am talking about, that should be applied to the stability value which will be obtained finally applying loads. So this is the table which we are dealing with. So in this table you can see that the stability correction ratios are there. So if you are using 63.5 millimeter height exactly for the specimen, then you will not have to apply any correction ratio, as you can see here, 1, for 63.5 millimeter or 2.5 inch is there, so no correction factor. In other cases, so if you get value of 30 kilonewton, for example, the stability value is equals to 30 kilonewton in your case, but the height is not 63.5, rather this value is say for example this is not the height is becoming rather you getting 57.2. in that case particularly you will be getting 1.19 as the correction ratio. So you will have to multiply 1.19 kilonewton with this value to get the original stability value. In that case, if it is not it, rather this one. So in that case, apply stability as this one. And from this chart, although I not want to discuss these things, these basic properties, as you can see, as much the height is decreasing, the correction factor is increasing. That will be resulting in higher stability ratio than the obtained one, just because of what? As you are getting less height value than the usual, so it will be obviously giving the lesser amount of value and result resistance. So original value, if it were 63.5 rather than 57.2, instead of 57.2, if it were 63.5, it will be exerting greater amount of stability. So that's why we need to multiply it with a value that will be greater than 1. And in case of if it is the height is the greater than 63.5, in that case we will have to multiply this with a value factor which is less than 1. That is, as this height is greater than 63.5, that is exerting you the greater value, and if it were exactly 63.5, the value of stability would have been decreased, and that decreased value will be obtained using this correction ratio chart. So that is one thing what we need to know. And another thing, while mixing, you will be mixing the bitumen, that's why you will have to heat it. So there will be two temperatures. One is the mixing temperature, another will be the compacting temperature of the bitumen. So you have to maintain these two temperatures, and for these two temperatures the guideline says that it should be 100. It correlates with the centistroke, the viscosity value actually. So it says that it should be 170 plus minus 20 centistroke, and the temperature will be relevant to this one, this viscosity, for the temperature for which this will be exerting the viscosity of 170 plus minus 20 centistrokes, that will be the mixing temperature for your particular asphalt. And the compacting, the guideline says that it will be 280 plus minus 30 centistrokes, and this 280 plus minus 30 centistrokes corresponding temperature will be the compacting temperature for your mold. So why you will be compacting after mixing? Well, when this will be mixture has been finally done, we'll need to make compaction to make this actual in shape. So after asphalt content is mixed over there. So for this, the thing we have discussed, the three types of traffics will be there, as we have discussed here. The guideline says that for light traffic we will be applying 35 blows in each layer, each side, the medium 50, and for the 75 blows in each side you will have to apply. So therefore this one, the heavy traffic, medium or light traffic is required for this. So while compacting, the temperature will be this one, the temperature which will be corresponding to this viscosity, and mixing corresponding to this viscosity you will have to maintain. So while maintain and after mixing, the compacting temperature will be learning this from the chart. So there will be another chart. I'm just showing you now. There will be another chart which I'll be showing you here now. If I import this thing, so this will be the chart which shows you viscosity in centistrokes viscosities in centi-stokes, as you can see here, in centi-stokes, and the temperature in Fahrenheit is already given there. So from this graph, this is the mixing range. If it is 170 plus minus something, the mixing range you can get from there, and 280 plus minus something, this compaction range. From there, these particular temperatures, these temperatures will be your particular temperature. So although you see that the mixing range, obviously the mixing, while mixing, the bitumen will be very much heated, and as much the time goes, the compaction will start, the temperature will be decreased. So these two values which you will be getting, that will be the final mixing and compaction temperature, which you must maintain while conducting the test and experiment. So after that, while compaction is done, the cylindrical mold, after that you will have to apply. After mixing is done, the compaction temperature will be maintained accordingly, and that time the compaction will be given in both of these two sides. So first of all, in this side you will be giving the compaction, and then you will be rotating this thing. After opening the mold, you will be changing the direction, and you will be rotating this thing, and then in that case you will be applying load in this direction, in this side, from this direction, as it will be rotated afterwards. So in both sides you will be giving the compaction. So if you are designing this pavement for light, you will be giving 35 blows, sorry, 35 blows in each side. So 35, 70 blows. So if this is for medium, you will be applying 50 blows in both sides, so 100 blows total in total. And for heavy traffic, you will be applying 75 blows in both sides, so both sides in each side. So totally there will be 150 blows after you will be applying the load. To make it further clarified, I will be needing a hammer. If I say I will be needing a hammer to make the compaction done, so the hammer will be 10 pound, or I can say it will be 4.5 kg in weight. The hammer, this thing, this is movable through this stick, so you will be picking it up to a specific height and then just release this. So this 4 kg, this height is nothing but 18 inch. Then you will be releasing it, and the blow number will be 35, 50 and 75 per each side. So after that you will be rotating this sample and again providing the similar amount of blows to make it compacted. So this says that make 3 specimens at each of 5 different asphalt contents. So one thing which I need to say you before going to anything, that we will be using 3 specimens for each of the 5 asphalt content will be using. The Marshall mix design says that the graph, initially the Marshall mix design, before refining, we have found that we were trying to make all this within the specific range. I will be showing you the ranges here now. I would like to show you the ranges here. So let's import the conditions here as well. So if I want to import the conditions, so these are the conditions which must be maintained. So blows, you will be easily maintaining this thing. You will have to ensure that the stability, if you are designing for light traffic, which should be the minimum 750 stability should be obtained. So if it is greater than that, then Marshall mix design is satisfying this criteria. The flow value, if you get that the flow value is within this range, then you will be taking the mix design as a satisfactory criteria. And the air void, if it is within this range, again satisfactory, and void field, if it is like this will be again satisfactory. But the problem created were before this particular method which we are conducting at present. What was the problem is the asphalt content was very much problematic from different portion, different region of the world. They have objected this thing to the ASTO authority that we are facing very much problems. We are satisfying all other criteria, but we are not being able to satisfy the criteria of percent of asphalt content. That percent of asphalt content is not going within the range, within the satisfactory range. So that's why what we are started to do, that from now we are first fixing the asphalt content. So we are taking 5 asphalt contents, and for your experiment as well you will be taking this thing: 4%, 4.5%, 5%, 5.5%, and finally 6%. So these 4 asphalt contents you will be taking, and for these 5 samples, 5 asphalt contents, 3 samples for each asphalt contents will be created for this test to be conducted, and from those average values of stability will be taken and all other things. So that's how you'll have to proceed. This is the Marshall mixed design. So for whenever the new convention has been made, that you will be first trying to fix this asphalt content for the, although the main purpose is the mixed design, as you know, the mixed design that will be indicating the process of an asphalt content should be determined afterwards. But for this particular test, we'll be initially taking these 5 asphalt contents, and we'll be trying to satisfy all other criteria. And if it is satisfied, then from the all of these 5 samples, for which content all the economic thing or all the other criteria satisfied, that will be our final mixed design. That is the new trend or new convention started after that, and finally it is just reducing the complexities which were arising before that. So that was a historical thing in this Marshall mixed design method. So therefore we are using asphalt content for before. So for 5 groups, you will be divided into 5 groups for this experiment, and 5 asphalt contents will be there. Then you will be calculating the gram value of asphalt based on the aggregate total mixture value, as we have seen, I have shown before. That's how you'll have to proceed. However, so that's how we'll have to proceed. Now these 5 asphalt contents, if you make, and you will be creating plotting graphs, and from graphs we will be try to watch that whether the criteria satisfies or not. So however, generally for using these 5 asphalt contents, all the other features will be meeting its criteria, will be watching afterwards. In general it satisfies, and if not, then you will have to do what? If you see that for this range of asphalt content, this is the fixed range of asphalt content, for this range no asphalt contents satisfies all the criteria for all other features, then you will say that in direct manner you will say that this particular gradation of aggregate, the used gradation, this aggregate sample will have to be changed. So just bring another sample and another sieve analysis of aggregate, different grade of aggregates we need to use for the construction of this particular pavement. Other than that, it will not be satisfied. So if not satisfied, then you will have to change the gradation of aggregates. So different grade of aggregates will be used, but asphalt content will be as usually always these 5 samples will be used. For 5 asphalt contents, each of these you will be using 3 samples. Okay. Finally, we'll be obtaining graphs like this. So what this was the criteria. So if you see that for the asphalt contents, which asphalt contents it meets all the criteria. If you get multiple asphalt contents for which all the criteria are satisfied, then choose for the most economical asphalt content combination, which will reduce your construction cost. So that will be our final target. Okay. While discussing about the methodology, about the experimental factors, the conduction, that I have missed many things, how the preparation of the aggregates bitumen will be done. Maybe I will not be able to cover all this thing in my lecture, just because of the shortage of the time. One class, it will not be enough. We don't have enough classes also for this semester as well, so I will be I might be ignoring some facts which you will be, I think you will be learning from the notes, or if manual is provided. Other than nothing to worry about that. From whichever I am just showing, you will have to learn these things, and based on this, your question in the final quiz will be appeared. Okay. Need to say about this thing that in previously we have said about GMM. If you recall this in your mind, that we have discussed about GMM. This GMM, how to determine this GMM. So while calculating GMM is the maximum specific gravity, and for this there is a specification D2041, according to which this specific gravity would have been used. But for our convenience, you can see that we have for our convenience we have made it shortcut. So we haven't used this particular method, that is, this is time consuming method, for which we haven't used actually this method to determine. We will not be showing, just because this will be automatically done before. But if you want to know, this is the designation according to which the maximum theoretical specific gravity for at least 2 asphalt contents will be evaluated before that, and average of that will be calculated for this particular value. However, so we are not focusing here further. We are going to the next thing. As we were speaking about the stability, as you can see here, can you identify which one is missing? Maybe unit weight. We generally don't have to worry about that. Another thing is missing. This is VA and this is VFA. But VMA is missing here, so there should be another table for VMA which we'll need to know, and the criteria must be satisfied. So for VMA, this is the table which we need to must satisfy. So their nominal maximum particle size, that is the nominal size which we'll be using. So for our case, we'll be using what, you know, the 19 millimeter in our case. So in that case, if we are using the design air void, which we'll be finding, based on that we will be saying this is 3% design air void, 4% design air void, and 5% design air void. From our previous criteria, you can see that always 3 to 5, 3 to 5, and 3 to 5 air void will be the limit. So whatever the air void will be finding, the void VMA will be automatically calculated for particular nominal size using this value. So if you have 3, then the VMA is automatically getting 12. So if you can satisfy VMA and if you satisfy these two, this VMA will be automatically satisfied as well. So from this chart you can calculate the VMA and automatically calculate the VMA, sorry. So if you find that VMA, the minimum VMA should be 12, this for 13, for 4, and in case if you find that the design air void you found it is in between this 3.5 or 3.75, then in that case interpolation of these two will have to do to get the minimum VMA, and you will have to check it with your obtained VMA whether it satisfies or not. Okay, so VMA, all the features, that's how we will be trying to show and see. So in some cases you might be watching some cases might arise like if we plot the curve of VMA, the VMA curve, as you can see here, the VMA curve, it will be like this. So there will be obviously a minimum VMA, as we have just learned from there. So minimum VMA will be there, say for example that is 12 in our case, for example. So in that case, in some cases this problem arises, particularly in case of VMA. If you see, this is the 12 of VMA, and this is minimum. If this VMA you are obtaining that is greater than this one already, then you don't have to worry about that. Just because of what? Just because you are finding that your VMA is always greater than, so it is irrespective of asphalt content, it will be always greater than 12 minimum value of VMA, so you don't have to worry about that. But in some cases, if you find that your range, the minimum range is there, but your VMA is beyond this, so in that case again you will have to change your particular aggregate gradation. In this case, just because you changing of asphalt content will not be giving or pushing this curve within beyond this particular minimum range, so it is all just because it is always less than this one, that's why you will have to change the gradation. This is depending on aggregate grade, that's why the VMA is not satisfying. In that case you will have to change the gradation again. So this might create problems sometimes. So after plotting this thing, you will be able to understand whether it is actually creating problem or not. Other than that, you have conducted a successful test. So however, okay, so how to conduct the bulk specific gravity test, when we have discussed about this in theoretical portions, the definition portion, the bulk specific gravity, for that the water should be immersed into the water, say at least for 24 hours. You should be immersing this specimen within the water. Then after that you can expect that the water is going through all the permeable pores, and that's why how you can take the value of WS, WW, all these things. WW you can directly take in the water, and WS, this is the SSD weight. After picking it from the water, you can dry the surface and take the saturated surface dry condition weight of this particular specimen, and the weight of air you will be automatically taking just before placing it under the water for 24 hours. Before that you will be taking the weight in air of this particular sample. So after conduction of the bulk specific gravity test or effective specific gravity, you can calculate from other values, so bulk specific gravity, if you have conducted the test, WA, WS, WW is finally obtained, then you can immediately go for the test of stability and flow. For stability and flow, as we have said, that the specimen will be kept like this, and over that and beyond this, two compressors will be used like this. So from this we will be applying loads and will be getting the stability and flow values. But before that, one thing you must need to understand, while conducting stability and flow test after bulk specific gravity, we will have to make sure that this particular sample is again immersed into water for at least 30 to 40 minutes. 30 to 40 minutes will have to keep it under the water, and there is a specific temperature range for this while we'll be keeping it under water. That is nothing but the 60 degrees centigrade plus minus 1 degree centigrade. That is very sensitive, as you know, and that's why also you can say 140 plus minus 1.4 Fahrenheit. So 140 plus minus 1.8 degree Fahrenheit we can also say. So any of this one. So this is the and again from the definition you know that the stability is corresponding this particular temperature and 2 inch per mean loading rate should be there. So that's why it should be immersed in water for 30 to 40 minutes and water bath which will be maintaining this temperature. And as you cannot apply the load with keeping this in water, so you will have to pick it from water, and immediately after that you will have to apply the loads, start the applying loads after completing all this arrangement, after removing it from the water. And if when after 30 to 40 minutes you will be removing the sample from the water and adjust this specimen and start applying load, this time should not be greater than 30 seconds. This is very sensitive again as well, just because you will have to maintain 140 degrees centigrade temperature, as you cannot apply it in the water. So after removal from the water and adjusting it in the specimen before the applying load, the time should not be greater than 30 seconds in between this one. That is also prohibited. These things you must have to maintain these things as well. So that is another thing what we have learned here. So by this time I think most of the things we have completed. So the stability value you will be obtaining, the flow value you will be obtaining, the unit weight you will be calculating actually again, then the VMA, VFA, all these things you will be again calculating from other data. So I think most of the things I have completed. As it is a very lengthy discussion is going on, I might be missing most of the things. I am not getting into the details of these things. One might ask you the question why it should be immersed in water 30 to 40 minutes. The rationale behind this is I need to consider the worst case scenario. As you all know that the problematic factor for bitumen is nothing but the water. So while it is submerged in the water, it will be exerting the most poorest case what you can expect from bitumen, this bituminous specimen. So that's why we'll be submerging it into the water for 30 to 40 minutes within this temperature as well. Not only for maintaining the temperature but also for maintaining or considering the worst case scenario in which it will be exerting the lowest possible stability, and based on which we can design that will be giving the lowest stability value, resistance value. That's why we are using this one. So there are rationale all over the experiments for each and everything, but I'm not going to discuss just because of the shortage of the time. Another thing one might ask you that why there is no chart for unit weight. Why? Just because if you fulfill all 5 other graphs, criterias, features, then this unit weight will be automatically satisfying the criteria. So you don't have to focus on that unit weight further. Rather you focus on these other 5 features, then it will be automatically coming into the within the specific or desired range as we are expecting. So I'm going to show you the chart now, table, which we'll have to complete. Also we have talked about this the sieve analysis, this one before, so you'll have to also complete this to get the nominal size, the maximum size, all these things from this. And after that this table you'll have to also complete. So the formulas I have provided here for your convenience. So first of all you will have to fix this 4, 4.5, 5, 5.5, 6. So 5 types you will have to use. All these things you will be getting, that is nothing but for 3 samples you can prepare for each of the contents to get the average values in each cases. So that's how we can proceed. So I'm just considering one instead of average for our discussion, convenience in discussion. I hope you will be able to understand all other things accordingly. Again, one thing I need to say here, while calculating bulk specific gravity, the procedure you'll have to follow, that will be nothing but the bulk specific gravity. There is a ASTM standard test, the ASTM D1188. This is the standard using which we can determine the bulk specific gravity, and I cannot remember what I have said before earlier. Bulk specific gravity test. For this you might be needing to keep the specimen in oven dry condition, to keep it in oven for at least 2 hours. I'm just summarizing things. To get the oven dry weight, possibly the WA weight that we are expecting, then we have to, while mixing the specimen while mixing the specimen, it will be according to the temperature which you'll be obtaining according to the centi-stove values we have discussed earlier, 170 plus minus 20 and 280 plus minus 20, 30. This centi-stove corresponding temperature. Say, if I make it easier for you, say it were from the graph I have shown you, the log graph, it were, as I can remember, from there you might have got the temperature for mixing maybe 148 to 153. This is the range which you must maintain for this, say in Celsius, although it were in Fahrenheit. So this is the range of mixing, say for example. So if it is the mixing range, then let's take the 150 degrees centigrade for our particular test. In this experiment we'll be mixing in 150 degrees centigrade, so that's why you must maintain this mixing temperature while mixing, and the mixing will be done for time 2.5 minutes. Mixing will be done 2.5 minutes, the bitumen with the aggregates. And after that, also this was for mixing criteria, this was for compaction. So in compaction, while compacting, the temperature range we might be obtaining 138 to say for example 142 degrees centigrade I have obtained. So let's take 140 degrees centigrade for compaction. So while compacting you must maintain this temperature, so the time is again important, so that the bitumen is in 140 degrees centigrade. You must maintain this thing while compacting. And compacting, as we have seen, the time required for the blows, the required number of blows, that will be the time of compaction. This is compaction. And this is mixing. This is mixing. And time for compaction will be the time which will be needing for the number of blows, as we have seen in both sides. And the remaining thing, another, what it was, the oven dry. I have already said about this. The oven dry. In oven dry condition, for making it make it to sense, so you must need to keep it in oven dry condition for at least 2 hours. And after that you will be taking the weight, then for bulk specific gravity you will be submerging it into water, then taking the weight for saturated surface dry condition. You will have to just dry the surface, keeping the sample saturated, as we have said earlier. So however, let's fill this table up. Specimen weight in air. So this will be taken, say for example you have found 11,000. The specimen weight in water, obviously it will be reducing, just because the specimen weight will be losing some equivalent volume of water. This was WW, as we have said, and this is WA, saturated dry condition. That will be greater than this value, just because, as if you can remember that we have discussed while discussing, we have said that in saturated surface dry condition here, WA plus the permeable pore volume of water is also filled with water in SSD condition, so this will be greater than WA in some up to some extent. So that's why this will be greater than 11. Say this will be 11 to 0, for example. Although okay, so this is SSD will be like this. And what will be GMB? GMB will be easily calculating from this formula as we have shown you before. The mixtures, the bitumen is bulk specific gravity of the mixture. Now another thing I need to say, the unit weight. How you will be calculating the unit weight? You will be directly calculating multiplying rho of water with the this specific gravity, bulk specific gravity of the mixture. That will give you the unit weight of this particular mixture, the sample you will be obtaining from there. So if GMB is something 2.7 something, then you will be multiplying this with this one to get the unit weight of this mixture. Then GMM you can easily calculate from this formula, although we know that GMM we have another designation which we have said just before this, that there is a STM designation for the determination of GMM. You see there, for GMM we have shown that for GMM there is a designation, but we are ignoring this for our convenience. In this case we can use this particular formula from which you can easily calculate GMM. Okay, for GMM, for calculating GMM, if you know the GMM, you can also calculate GSE as well. You can also calculate GSE as well. So first of all, vice versa, if you know the GSE, then you can calculate GMM. If you know the GMM, you can calculate the GSE in other terms. Also, if GMM can be obtained as we have said, the formula D2041, accordingly you can calculate GMM. So from this is the similar equation, just transformation, nothing else. So PS is 100 minus PV, as 100 is PMM. Okay, so PMM 100, so PS will be deducting the bituminous portion from the total PMM 100%, and PS from there you will be able to calculate PS. Then GSB you will be calculating using this formula, where G1, G2, G3, all these three will be known from previously known. So while you will be getting data, you will be knowing the specific gravity, bulk specific gravity of it. Obviously bulk specific gravity of dry, coarse aggregate, fine aggregate, and MF. So these three you will be automatically known. So using these three for aggregates and mixture, both these things we have discussed about the concept. That's how. But in while we are showing you, we are exhibiting the experiment in front of you, then in that case we generally obtain these values before and just give it to you to use for this particular test, as this test is very lengthy. Other than that, it will not be conducted in 1 week or 1 day, 1-2 days. So that's why we generally provide the data for you. You can use this to calculate the GSB from there. And what about the percent VA? Percent VA, you can easily, the percent of air void in the aggregate, you can easily calculate it from using this one. I can derive all these equations can be derived accordingly, but due to time shortage I am not going for further detailing, rather I am just showing these things in front of you. And percent VMA, so volume of the mineral aggregate void in volume of void in mineral aggregate VMA. This is nothing but the 100 minus the GMB minus multiplied by PSG divided by GSV. That is actually giving you the total portion of air void in the combined aggregates together. And the VFA, as we all know, that is the volume filled with asphalt. And this volume filled with asphalt, so volume of void filled with asphalt is excluding the bitumen, excluding the absorbed bitumen from the total bitumen content, that is VFA. And that is nothing but the total VMA, that is the total void in the aggregate minus the air void existing. So this will give you the volume of volume filled with asphalt. And if we divide it by percent VMA, then we will be getting the percentage of volume filled with asphalt accordingly. So fill these two things. Then height of the specimen, if it is 63.5, then no correction, 1 will be applied. So 1 multiplying with the stability observed, if it is in pound, if it is 750, then it will remain 750. Other than that, you will have to apply the correction factor. If it is not 63.5, then you will be obtaining the correctified stability value. And the flow value, there you see 0.01 inch unit, you will be directly putting these values here. So you will be completing the total table, and after that for five groups of data, you will be plotting using this data. You will be plotting these graphs, and from these graphs you will be watching whether, say for example, I have 5 data like 4 to 6, 4 to 6, 4 to 6, 4 to 6, 4 to 6. So I have data like this: 4 to 6, 4 to 6, 4 to 6, 4 to 6. Okay, so we will be comparing this with our values. We will not have to focus on this one, rather it will be automatically satisfying if all 5 others will be satisfying there. Air void will be trying to know, as we know that the air void is the acceptable range is 3.3 to 5. So we'll have 3 to 5. So 3 to 5, this range will be determining whether this is satisfying. So let's say 3 is satisfying, or 4, this 4 is satisfying, this is not. So we will be trying for these 4 ranges whether all other is satisfying this range or not. This is well above the 12, so all these 4 will be obviously satisfying this one as well. So in case of VFA, there might be another criteria. We'll be try to see whether this 4 is satisfying or not. In all cases, even the stability value, the minimum stability value is there. So if it is minimum, we will have to see whether this say these 2 only satisfies this. So from there, these 4 we have found, and there we have found remaining this only these 2. So this 2 is only available now. Then for the flow value, if we see that the flow value is within this range and this 2 is satisfying, then from these 2, which one you will be taking as the final asphalt content. Say this is 4.5 and 5. So from 4.5 and 5 you can take any one of these, but depending on the economical point of view, if you find that that 4.5 or 5, whichever will be economical, you will be choosing this for the final mix design, and that will be our final task for this particular experiment. And if you find no asphalt content is satisfying, any one of these graph is just going out of the specific or desired range, then you will have to say that I have to change the particular gradation of this aggregate. Using this aggregate, you cannot satisfy this mixed design. Rather, we'll have to choose different grades. Then we'll have to try this again and finalize whether this aggregate sample and the particular asphalt content is okay for this mixed design or not, and that's how you will have to proceed. I think I have completed all these things. The mixed design, very lengthy lecture today it was actually, but I hope in short I have tried to cover all these things. So if you have further queries, you can ask me. I will be trying to give you answer, but before that I think I have shown the basic concepts. I have proven it in front of you. So thank you for being with us. Thank you everyone.